back on track. So let me recap. I don't know what happened, but it was not even letting me connect again on Facebook. But now we are back, and I'm glad. I thought of a cyber attack actually. So it is. So you split the DFTs into two parts. Use half of the points here, half of the points here, and you take n by 2, n by 2 point DFT. It's very simple to understand. And then you combine, and once you are combining to get an 8 point, 4 you don't get any saving, but where you have the fourth index, because G4 is same as G0, so you don't have to recalculate this, and this is where the savings are. Like you are not recalculating it, so this results into saving, and then but still you need to have this W84, this factor, total factor, which you have to compute, and then you have h of 0 instead of h of 4. Okay, similarly you have x of 5, and you do g of 1, which you have already calculated, plus W85 h of 1. Again you save. So you see the savings you are getting by a simple split of this, and using the fact that as DFT is periodic over 2 pi and DFT is periodic over n. So you are getting this saving, and x6 is G2 plus W86 H2, and the last point x7 is G of 3 plus W87 H of 3. So this part is all saving. Okay, and then Kuli Tuki thought that why even to stop here, because this is an independent FFT DFT and this is an independent DFT. I am taking this 4-point DFT, and I even don't care. Once I am taking a 4-point DFT, I don't even care that they are actually part of a bigger 8-point signal. All I care is I have these 4 points, I have to use DFT formula to calculate this. And so they thought about it, so why not even to, why should I calculate even the 4-point? Why not I further split it into 2 parts? Split this into 2 parts. 1 I keep here, 2 I give it to this, 5 I keep here, and 9 I give it to this. Similarly this minus 1 I keep here, and 3 I give it to this, and 0 I keep here, and minus 2 I give it to this. Now I have 2 points and 2 points and 2 points and 2 points. Okay? I thought, why not to calculate the 2 points and then combine them using the same formula, and then we have 4 points, combine 4 points into 8 points, and if we have 16 points we can divide 16 into 2, 8, 8, and then 2, every 8 into 2, 4, 4, then every 4 into. So this is what the trick they use, and it's a simple but an amazing trick of splitting the first an 8-point DFT into 2 4-point DFT. So this is, you have an 8 points, so you put 4 points here, index x0, index x2, index x4, 0, 2, 4, and 6. Okay, calculate 4-point DFT. So you get G0. So this is the notation we are using. You get G0, you get G1, you get G2, you get G3, because we are calling these as G of n. 4 points. And similarly, you have 4 points here, which is x1, x3, x5, x7. So you have h0, h1, h2. So this is very simple. Okay, let's just do it 4 points, but as I mentioned earlier, you can split it further into 2 points DFTs. So this, now you got to combine to get x of 0. So x of 0, you need a g of 0, you need w8 of 0 and h of 0. For h1, you need g of 1 and h of 1, and you are combining it using the twiddle factor. So if you try to plot this, you have, this is g of 0, this is h of 0, and you take this h of 0 up, okay, and remember the signal flow notation. This is a multiplication, so you would multiply it with w8, 0, and add them up together, you get x of 1. Okay, similarly, you have g of 1 and h of 1. You take this h of 1, w8, 1. Then you have g of 2. So I'm just combining as is given in the formula. Nothing fancy about this. Just using different colors so that you get the feel of it. w8, 2. Okay. And then finally for this you have w8, 3. Okay, so this is your x of 1, this is your x of 2, this is your x of 3, this is your x of 4. And now are the savings. The savings are for calculating x of 5. You don't need to calculate g of 5 or and h of 5. Rather, you bring it down, okay, and this is where you get the butterfly structure. You bring it down, bring it down, bring it down, and here is the pure multiply, which is w8, 5. Okay, and this structure in signal processing, which is this, and this is called a butterfly. Okay, so this is very famous structure in signal processing. It makes like a butterfly. I fly like a butterfly. So this is a butterfly. Okay, so you have G0 and H0 used twice, and you also see the saving to calculate 2 of the points of the final DFT. Okay, and similarly here, once you bring this down, bring this down, and bring this down, and bring this down. Okay, and here you have to multiply it with a twiddle factor, which is w8, 7, w8, 6, and w8, 5. So you see 4 butterflies. 4 butterflies. One is, this is the other butterfly, you see, and then is another butterfly, you see here, and you see I have another color. So, so you see 8 butterflies. 8 butterflies, a butterfly structure. So let me just recap this. So you have 4 points, 8 points, 8 points. You split half here, compute 4-point DFT, 4-point DFT. This 4-point DFT is capital G, and this 4-point DFT is capital H. And then use these to calculate first 4 points, and then use the same set to calculate the next 4 points. So So by doing this, you get a structure which is called a butterfly structure. And but I just mentioned that even these 4 points can be split into two points DFTs. Okay, so there is no point in taking even the 4-point DFT. So interesting, like you have x0. So once you split, you have 4 of these. 4, 1, 2, 3, 4. You give x0 to this one and x2 to this one. Then you give x4 to this one and x6 to this one. And similarly, you give x1 to this one and x3 to this one, x5 to this one and x7 to this one. Right? So calculate two points, 2 points, 2 points and 2 points. Okay, so what is the formula of 2-point DFT? This is important. What is the formula for 2-point DFT? And we know the formula. The formula is same. X of k is equal to, if we are taking only 2 points, so there is n0 to 1, x of n exponential minus j 2 pi k n over 2. So this is the formula. 2 cancels with 2. So we open this up, we get x of 0. And because n is equal to 0, exponential of 0 is 1, so it is x. And x of 1 exponential minus j 2 pi and k. So this is x of k. So now we have 2 points. X of 0, put k is equal to 0, you get x of 0 plus exponential of 0 is 1, so x of 1. So first point you calculate by adding 2 samples, and the second point you calculate by, because once you put k is equal to 1, exponential of, sorry, this 2 has gone away, exponential of minus j pi is minus 1. So the second sample you calculate by subtracting the 2 samples. This is all you have to do in calculating the 2-point DFT. Like you add these 2 samples together and you subtract these 2 samples together. Add these samples together and subtract these samples together. Add these samples together, subtract these samples together. Add these samples together, subtract these. This is all you have to calculate actually. Adding, subtracting, first splitting it, no matter how big a signal you have, into two points DFT. And 2-point DFTs can be calculated in a very simple manner, because the formula says a 2-point DFT is once you add and the other time you subtract. So you add, you subtract, you add, you subtract, you get. Now all you have to do is you need to combine these and using the same formula, where what do you do for that? You take this up and this thing you multiply with W40, and you take this up, you multiply this W41, okay, and then you bring this down to make it a butterfly, W42, and you bring it down and you have W42, okay. So this is the box which we earlier marked as 4-point DFT. So you get 4 points of G0, G1, G2, G3. So we were calling this as G0, G1, the same, G2 and G3, and now we can combine them together. And similarly here, you combine this, and you do this, and this. So butterfly, 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 so many butterflies. Same. W40, W41, W42, W43, and W's have some relationship with W4 has a relationship with W8. It's a simple relationship. You multiply both with 2, so this is W82, and because you don't have to recalculate all these, you can use the same one. Here is W4, W8, 4, and this one is W8, 0, 2, 4, and 6. Okay, so means that, and then you are going to combine these, as I need not to redraw this, but you already know this, and you have to bring it down here. This is the one butterfly, then you have another butterfly, then you have another butterfly, and then you have the last butterfly. So if you look at an FFT, and I'll be showing you in slides as well, all you see are the butterflies. So you split this into two point DFTs. Okay, so simple that if you are taking a discrete Fourier transform, and this algorithm is called fast Fourier transform algorithm, which splits your signal into two points. And but you know, the challenging part of using a program to calculate is these indices, very scrambled. This is actually called decimation in time, because you know, the pointers, you can use just pointer plus plus, you go to the next address and next address, but generating these addresses, because if you have 8-point addresses are like these, if you have 16 points, you will have your 0 and 8, and these will change, and then you have 32 points, 64 points. So generating these addresses is not that simple. Okay, it's not that simple, because if you end up spending a lot of time in calculating the indices and then using them to do the two points, then there is no point in all the savings you have here, because you got to calculate the indices to fetch the data. So one of the challenges of finding fast Fourier transform is to somehow generate these indices. Okay, and people must have been thinking, and especially the hardware designers or the designers of the digital signal processor chip, and this I find more even interesting than the DFT algorithm itself. Okay, how do you generate these addresses? And so simple and so interesting to generate these addresses. Let me tell you, and then we'll take a break. So addresses are, you got to generate them in this order: 0, then 4, then 2, then 6, then 1, then 5, then 3, then 7. Okay, this is the order in which you have to generate the indices. So somebody must have thought about this and realized that this is simple, very simple, that you have an adder, okay, and you put it in a different way, that instead of adding 1, once you do plus plus, you add 1 here, and instead of propagating carry in this direction, propagate carry in reverse direction, and you can generate these indices. Okay, so all you have to do is just plus plus plus, add. For example, once you add 1, 0, 0, 0 is the first index, so this is the index. So you add 1 here, not here. And if there is a carry, you don't propagate it, you propagate it in reverse direction. So let's see that. Okay, so you get 1, 0, 0 in binary, which is 4. Then you add 1 here. So 1, 1, 0, 1 carry, you take it on this side, it becomes this, which is 2. So this is the index. Then you add 1 here again, so it is 1, 1, 0, which is 6. Then you again add 1, 1, 1, 0, 1 carry, 1, 1, 0, 1 carry, so 1, which is the next index. Okay, so 0, 0, 1. Okay, then you add 1, which is 1, 0, 1, it is 5. 1, it is 1, 1, 0, 1 carry, 1, 1, which is 3. Okay, then you add 1, it is 1, 1, 7. So simple adder, simple and adder, a full adder, where the carry is propagated. You must have learned about full adders in your logic design course. It's a simple adder, but the 1 is added on the last full adder, and the carry is sent back to the full adder you put here. Okay, so this generates, no matter you know whether it is 8 point or 16 points or 1024 points, like even if you have like 1, 2, 3, 4, so this is for the 16 points. So you add 1 here, you get 1, 0, 0, 0, which is 8. Then you add 1 here, it is 0, 1, 0, 0, which is 6. So you can generate all the indices. So every digital signal processor, every chip you buy, the one which you are using in the lab as well, has bit reverse addressing mode. If you enable that and you say pointer plus plus, okay, pointer plus plus and enable bit reverse addressing. It is called bit reverse addressing. There is a mod in digital signal processors. If you enable that mod and do pointer plus plus, it will do this, and also pointer minus minus, it will do this. Okay, so a neat way of generating these indices is you still do pointer plus plus, point your pointer towards the first value, and once you do pointer plus plus, it will automatically be 4. And if you do pointer plus plus again, it will automatically be 2, and then it will automatically be 6, then 1, then 5, then 3, and then 7. So bit reverse addressing would automatically generate these indices. So you solve one big problem in digital signal processing, which is to handle this odd way of addressing, and then you use the power of this FFT algorithm, which reduces the time of computation of DFT into something which is very, very little. As a matter of fact, instead of calculating 1, you can perhaps calculate 100 of those DFTs if you use this algorithm. 100 of those DFTs, 100 times faster, even perhaps for 1K point DFT computation. So fast Fourier transform has really transformed digital signal processing. But if you go and look at it, it is such a simple trick which Cooley and Tukey used. So once we come after the break, I will show you the original paper and then some other algorithms which people tried to use for computation of DFT. And remember, today we also have a quiz. Please call everybody that there will be a quiz on LMS. Dr. Ali has prepared that. So let's meet after the break, 5 minutes break, and we then go from here.